see my stack of papers?
Let's go ahead and get started. So today we're going to finish up on caching. We're going to basically talk about virtual memory and how the hardware can aid the operating system in separation of users, which is also very important to understanding Meltdown and Spectre.
Is this going to be on the midterm?
Yes.
Okay.
So we'll finish up with memory, virtual memory. Caches with virtual memory. Then we'll talk about your midterm review, and then we'll go into your ethics paper afterwards. So we got 3 things, but hopefully they're going to be pretty short.
I hope so.
As a quick review, because I know caching can be confusing at first, let's at least go through the set associative example, which really brings together caching all together. First, let's go ahead and step back. Why do we have caches?
Because pulling from main memory is really long.
Right, and pulling from caches is very
Fast. Go fast.
Gotta go fast.
David. Let's see you even respond to that now.
What? Sorry, we're
fast.
talking about coffee over here.
Like
Coffee? Oh, okay.
Go faster. Okay.
How do you make tea?
How do you make
keeps
tea?
Going and
How
going.
do you make tea?
Oh, I just you get a T-ball and put
Yeah,
loose leaf in it, and then there's
got
a,
the auto guys and humans
what
like,
was it, one of those water dispenser things that has a little hot tab, and I just put it in there. It's easy. It's easy. It's not the best, but it's easy and it's good. It's better than the tea bags,
Don't fall
that's for
asleep.
sure.
If you fall asleep, I'm gonna fall asleep.
Disgusting.
All right.
No, you're not.
I hope everyone had a good spring
punch
break.
Yeah, how was yours?
Please.
It was great.
Yeah. Did you go anywhere?
No. I had a lot of things I had to fix in the house.
Oh, okay. That's
Nice.
a spring break.
Yeah.
Honey to-do list? Honey to-do list?
Oh yeah, that always grows, I've noticed. It doesn't shrink. It's weird.
Yep.
It's funny how that works.
Yeah.
I baked all Saturday.
All right. Hopefully everyone is rested after daylight shavings.
Shaving.
Shavings.
Daylight shaving.
I actually took my clock out and I went up to my kids and I go, "You're about ready to lose 1 hour of your life." How do you feel?
My car clock is finally right.
That is sad.
That's good.
I can't
Nice.
change it.
That's
the hour
like
button
never
doesn't-
taking down your Christmas lights, right?
The hour button doesn't work, so I can't change my time.
Oh no.
So I literally half of the year it
What you
doesn't
could
work.
do is wait till it's noon and then disconnect your battery, right?
I'm not disconnecting that. I have enough issues with my car right now. Apparently there's a new security issue that popped up with my car.
All right, so good introductions. Let's go ahead and get started on the material. So we're loading to register 1 from memory 1. What happens first? It's a cache miss. So what happens after the cache miss?
Load in from memory.
Pull it.
0 and 1.
Right, and where is that going?
The first one.
The first cache line, right?
Yes.
And then you're going to change the thing.
The reason for that is if memory address 0 in binary is 0001, so the set is that third 0, which would be up here, and then 1 would be the offset, and the preceding 2 zeros are the tag. Okay. How about register 2? It's a miss. What happens?
It loads it into the second one.
In the second cache line.
Yes.
There we go. Now why is LRU pushed back to the first cache line?
Because it's the only other thing that was loaded.
And it's the least recently used of that cache set.
E.
So if there are 4, remember it would be the least recently used of that cache set. Okay, 4 cache lines. All right. Now we're going to store to memory 7 from what's in register 2. Well, what happens?
Do you need to pull it first? 'Cause it's a miss. No.
Actually, is this
Wait,
right?
is this right through or right back?
You mean right allocate or not?
allocate.
You know, I don't remember.
I don't know.
It's right allocate.
Right allocate.
Okay.
Allocate.
It's
Good catch. Good catch. Yeah. So this is right allocate. It pulls in 162 here. What's it? Register 2, 150, and then wrote it to the second block.
Yeah.
Yeah. Of that cache line. All right. And why is that cache line dirty?
Because it changed
Because
it.
it's different and the memory.
It's different than memory. Yes.
Yay.
Namely, we've written to it.
Oh.
Magic.
Now we're going to write from register 1 into 4. Is that a hit or a miss?
Miss.
Oh,
No,
that's
that's
Nope.
a hit.
It's
That's
a hit. Right, because it's going to hit right here onto that 71.
Yeah.
Notice that it changed the value there and put the dirty bit on because
Dirty.
now this is not the same as what's in memory.
Sorry.
Woo! Alright, we're going to load from memory 0. Is that a hit or a miss?
That's a hit.
It's
Hey.
a hit.
Yay.
Is L or U going to change?
Yes.
Yes. Yeah.
Sorry.
There you go.
I forgot LRU was for a second.
Least recently.
Eviction notice.
I was thinking the V.
And then we're going to load from memory 8.
Where's A?
No, it's not.
No, it's not.
It's a miss.
It's a miss.
So the LRU is gonna change.
Whoa, whoa, whoa,
Wait,
whoa,
it's
whoa,
first
whoa.
gonna push it to the
Right,
thing.
we have to evict the second cache line.
You gotta push them back
Gotta
to the
evict them
memory.
back to memory. And then we pull in the
change
other
it.
one. Yeah. Alright, so
Magic.
we evict him
Boom.
and we bring in the next one. And then, well, it
The
The
doesn't show it.
LRU changes.
The LRU
and
changes.
Then it goes
And the
to.
side changes.
Alright. Everyone good?
Yeah.
Alright, so let's go and fast forward.
Whoa.
I was
We talked about instruction caches.
Sure.
Let's skip this pipeline thing. Good.
I think we understand pipeline.
Alright. So here's back to the memory hierarchy, namely cache SRAM. It costs a lot, but latency is low, and you have fast access, as opposed to disk storage, which is a low cost and high latency. Alright, so the problem, DRAM, well, I should change that to terabytes now. Yeah, yeah, we want our programs to work, even if they require more storage. We also don't want a program with 512 megabytes to stop working. We try to run a machine with only 256. We need more than one program in the machine. All right, let me make sure this problem makes some sense.
It's expensive.
It is too expensive to buy a lot of, but we want our programs to be able to run multiple, we want our computers to be able to run multiple programs at the same time, right? Or at least seemingly at the same time. Well, let's say for the sake of argument, your machine only has 512 megabytes. Just work with me for now. Work with me for now.
Yep.
And if each of your programs consume 256 megabytes of memory, but you want to run 10 of them, would this work out?
Nope.
No.
Not exactly. Well, you still want your program to run, so you need to come up with a scheme in order to alleviate this problem. How do you think this can be done?
Make humans less impatient.
Make humans less impatient. That would solve so many problems. Is that going to happen?
No.
No. It's like changing the speed of light, right?
Yep.
Yeah.
We can try. It ain't gonna work.
It's not going to work. Any other ideas? You've taken this course before, haven't you? Maybe. Okay, solution 1. By the way, big hint, solution 1 is always terrible.
Yep.
Just so y'all know.
I like solution 1.
Leave it the problem to the programmer. Oh, okay. So
No.
every time you write the program, you have to account for every other program that might run on your machine and be able to switch out memory.
Yeah, no.
Program must not make sure the program fits in memory or break the program in pieces so it does not into pieces that do fit and load each off to disk when necessary. Actually, it ends up not being a bad solution for some domains, especially video games, because you're really only running one program. You might have a couple of micro ones on the side, but you're really just running one program the whole time. So this is not actually that bad of a deal. Some cell phones work this way, although nowadays it's been pretty much moving more and more away from cell phones into more robust systems.
Mini computers.
Yeah.
Yeah.
Yeah. All right. So, terrible. Solution 2, slightly better, but not quite there.
It's always solution 3.
Another solution 3. By the way, DOS worked this way as well, which is great. Because then you can just overwrite whatever you wanted. So, 2, overlays. Little automation to help the programmer. Basically, give the programmer a library to help them solve this problem. Two pieces of code data may be overlaid if they're not active. This makes way more sense with the picture.
Yep.
Whoa.
Yeah.
Yeah. So each
I got
of
it.
these 3 columns is a program and what memory it can consume. So it can consume some basically green here, purple. The idea, of course, is that, well, yeah, as long as you're only operating up here, then you can kind of share this block with other programs, and if someone else needed that memory, you'd have to write all purple, to the disk. So the idea is that it would break it up into regions. The compiler would give you some code to work with, and you could at least chunk it out to different pieces. You would, when you wrote your program, you'd say, I consume this piece and that piece, and then you would automatically have a library saying, oh wait, someone else is using this, let me write them off to disk, and then you can use that piece of memory. So it's just really automating the problem, helping them out a little bit, but it's still not a solution we want, because we don't want the programmer to have to be worrying about multiprocessing all the time. Welcome, Jonah.
Good morning.
You're on standard Jonah time,
Yeah, I know.
despite daylight saving, so.
Yeah.
Do you get
Technically, I'm like 40 minutes early.
Playing Fortnite last week?
Okay, so option 3, which is what we do.
It's always option 3.
Always option 3. We build new hardware and software that automatically translates each memory reference from a virtual address, what the programmer writes, to a physical address. What's nice about this is the programmer does not need to know anything about how his program's laid out in memory. He just writes his program, and then the hardware plus the operating system take care of the rest. So, for example, all your programs will be written with a virtual address. They may all have the same virtual address, by the way. But when your program is loaded and starts running, the operating system, whenever you do a load, will translate that into a physical address of where it's actually being stored in memory. This allows the operating system to actually manage all the different chunks inside of main memory to where your programs reside. Does that make sense, high level, what's going on? All right. So a virtual address may go to this physical, or maybe it goes to part of the disk, right? But the operating system is going to have that recorded and allow you to translate it. Another nice feature of this is if you only have 512 megabytes and your program needs 2 gigs, your program is still going to work because the operating system is just going to offload that extra gig and a half to the disk, and the programmer, it doesn't matter. It still works, well, it's not going to work very well because you'll be hitting the disk all the time, but you don't have to rewrite or reprogram your software.
It's going to lie the same way to all the other programs.
It's going to lie the same way, right. As long as it's like coding. As long as you misspell everything
The same.
consistently, you're fine, right?
That'll.
Right? Yeah.
Yeah.
until somebody spells it right,
And then someone spells it right, and
and then you gotta fix
Pedal.
it.
then someone's got to fix it, or just tell the programmer that he's wrong,
Pedal.
right?
Yeah.
Or she's wrong. You're good, right? I think that's fine. Okay.
Is that really cool to you? So
Virtual memory enables multiple
Right.
programs to share the physical memory without knowing about each other's programs. It's called transparency. So the execution is transparent to other programs. Or worrying about modifying the data contents of another. Hey, this is protection. Think about that. That means that one programmer can't, hopefully, read the contents of another program that's running.
That'd be a bad thing.
That would be a bad thing, meltdown Spectre. That wouldn't be good, right? That'd be bad.
oh, sounds fun.
It does sound fun. Hopefully, we should get to that at the end of the course. All right, again, virtual memory. We have hardware logic to help and operating system software. Operating system. What's
Hardware,
Sardware? I call it
Sardware.
sardware. I wonder what sardware is.
software, and hardware
Software.
mixed together.
Yeah, that's it. Thanks. Nice. Well done. That's what I should call it. It's sardware.
He made a new word without even trying.
It's not ready for that one. Actually, that is our actual next research. If you do read in architecture, what they're doing is they're trying to associate assembly code with regions of memory that automatically run when something happens in that memory address. So I guess, yeah, that would be sardware.
Terrifying.
Interesting.
We have to stop that.
We had to stop
We've gone too far.
before the machines take over.
Yeah, that's how Skynet happened.
Guys, that's how Skynet happens, right?
It's already happening. It's happening right
Okay, so keep in mind that we're starting to come at the edge of this course because we only are concerned about the hardware. In operating systems, you'll talk about the software, which is going to take But I think here is where you need to keep a little idea about how we finally connect up with the software side of things.
Forward
So-
to that next semester.
Yeah, oh, it's gonna be fun.
I'm just glad it's not an 8 a.m.
I'm just glad it's with you and not
That
the other
too.
professor that I'm
So, virtual memory. Treat my memory like a giant cache. That's the idea. Any misses go straight to disk because you're going to store it to disk. How do we minimize disk access? First question: why do we want to minimize disk accesses?
Takes
It takes a long time.
Yes.
People are impatient.
People are impatient. Thank you. Yeah, it takes forever. We could buy lots of memory,
Gross.
You gotta live
but
while you
that's
can.
not always an option.
You can
We
wait
could
on
try to
memory all the
exploit
time.
temporal locality.
Oh, we don't
What does that mean?
What?
What?
Temporal
That's
locality.
like the whole.
Space.
I mean, it's fully.
No, no, that's space-time
Frontier.
continuum. That's Star Trek. temporal locality.
It's like the whole fully associative set of space.
Right, but how does that help? What does temporal locality mean?
You,
No,
you.
temporary.
It's like
No.
It's like
No.
At time. This is temp.
Spatial.
I don't know.
So if you access a piece of memory, are you more likely to access that piece of memory again in the future or
Yes.
less likely? Yeah, you're more likely. So that's what temporal locality is trying to.
Also, then the memory around it too at the same time.
Now the memory around it is spatial
Spatial.
locality,
Which is the next thing.
which is the
Yeah.
next one. That's what you did with your block offsets.
Right.
So that you increase your block offsets to take advantage of spatial locality. With temporal locality, that's where
You store it.
yeah, you want to store what's most recently used. Notice I used most recently used, not least, inside your cache. So that's where the direct map had the biggest problems with because it can only store one piece of memory in it. Or I'm sorry, yeah, one cache line represents multiple pieces of memory as opposed to multiple cache line representing multiple pieces of memory. And then lastly, do we use write back or write through for our virtual memory? If we're trying to avoid writing to disk,
Right.
Right back.
write back, yep.
Yay.
All right,
That's the dirty bit.
The
Yes.
dirty bit.
the dirty bit. Okay, hey, this looks familiar, right? Blocks. Okay, it's like caches, but instead of having blocks, we're gonna have pages. All right, whoa, everyone still with me? No.
So,
I'm out.
I quit.
All right, virtual memory is called pages and not blocks. So a virtual address consists of the virtual page number, aka your tag, and the page offset, aka your block offset.
Hint, hint.
Yes. Nudge, nudge. Misses are called page faults. Have y'all heard that word before?
Mm-hmm.
And they generally handled as an exception, aka the operating system has to come in and take care of it, which means it's going to take forever.
Me.
yay.
Okay, so this is the idea.
Oh god.
It's not that bad.
My legs.
You just don't like arrows, do you? You don't like arrows
I
that
don't like the
cross.
color choice.
That too.
If I give you, these slides are on GitHub. If you want to change them up for me, I'll definitely accept your
I ain't got
changes.
time for that.
Yeah, that's what I thought.
I just don't like, I don't like the blue on the purple. It looks
Wait,
weird.
is your
You-
company hiring?
Nope. I mean, I always accept volunteers.
Oh.
Intern.
Intern, yeah, unpaid interns.
I'm in the computer science field. That doesn't exist.
Yeah. Don't fall for the medical side of things. Always get paid for your interns here. Okay. Virtual address. If it's in physical memory, notice you have the address is in this block. Jump over to that block. Hopefully this makes sense. Hey, look, the orange one goes down to disk, and then if you access something in the purple, what do you think that means?
That sounds like a page fault to me, right?
Yeah. It means that it is a page fault, yes, but
So do not touch.
that memory has not been allocated for this program.
Gotcha.
So if they try and read and write here, the operating system, it's a page fault, the operating system has to go in and actually allocate that memory for the process. So notice that their virtual address space is already broken up into blocks. Initially, it has nothing allocated. And then once they reference memory, it causes a page fault, and then they load in that memory. Yeah, it's kind of funny. You load your process in, it finally loads the code into memory, sets up the environment variables, hits run, and then the second it says load, causes a page fault to load the data into memory, and then it can go ahead and start. That's just how it works.
Really complicated.
Oh yeah, operating systems are,
Not
yeah.
fun.
Sounds
No,
really
they're fun,
backwards.
but they are the most complex piece of software.
Oh joy.
Yeah, not my thing.
Not my cup of tea.
I could use a couple.
All right.
now.
Page table contents.
Components.
Components.
I must be tired today.
It's that hour, man.
It's that hour. Yeah, that daylight savings always gets me every time.
Daylight shaving.
I'm gonna call it that from now on.
Is that what it is? They just shave an hour. Especially in spring, it's brutal.
We should add like 10 hours.
Just
That's
randomly.
Just always add 10 hours.
We should just, go halfway in between 30 minutes and call it even, right?
Yeah.
And then just never adjust
Just
it.
never adjust it, yeah. But
We
then,
don't
what
need
do
it
I know?
anymore.
Yeah, we don't need it anymore. Actually, the one I liked the most was just forget time zones. Everyone's on Greenwich Mean Time, and then just make up your own times from there. I'm like, yes.
That would be pretty nice too, because then you wouldn't have to think about the time change.
Yeah, and I mean, I don't mind if something starts at 5:20, or I'm not 5:20, but 7:20 as opposed to 7 or 7:30. That's fine.
Well, and then the whole thing about, I don't mind sitting there saying that it's 6 p.m. or
Yeah.
Right,
what is
the
it,
middle of the
1800, and it's like actually 2 in the morning.
Yeah.
Like that would be.
Oh
okay
yeah, no,
with
the
me.
the military uses what's it called, Z time, which is Greenwich Mean Time. So
Yeah.
Anyways,
It's
virtual
24
page
hours.
number indexes into your cache, which gives you the physical page number, and then the block offset comes at the end. Hey, look, it's the same thing. The page table register just tells you where this exists in main memory. So think about that for a moment. When your program loads, it has the addresses up here. It takes a virtual page number, adds it to the page table to get to the offset inside of main memory where the actual address of it is stored. Then it pulls that physical address down, appends the page offset, and then can do the load. Does this increase or decrease the speed of loads and stores? Or does it slow it down or speed it up?
It exploded my brain.
Probably slowing it down.
Right, because now you got to calculate the page table plus virtual page number, so that's an addition. Then you have to jump to that memory location, so you have to do a load in memory to load the correct physical page, so then you can finally do your actual load that you wanted to do back then. So now every load is 2 loads.
Only if you had a miss.
And that's only if you had a hit, correct. If you had a miss, then the operating system comes in and just takes forever. Yeah.
This doesn't sound fun.
Well, we'll talk about it. So so that's it. Just an example. This was the programmer's address, jumps into the page table, gets it to the physical address, and that's what it actually needs to load from. So there's now 2 loads. On the other hand, if it's 0, meaning it's not valid, it's a disk address, causes a page fault. This is what it does: stop the process, page to replace, write back to data, get reference page, update the page table, reschedule the process.
Oh, God.
Does that sound like something that's fast?
Nope.
No.
Terribly slow.
Too many. Cut it down to like 1.
We just did one step.
Yeah,
Yeah, that'd be-
just stop the
Is that like
process.
abridging
No,
the
just
dictionary
stop
to
the
one
process.
page?
Just give up.
Let's just do it. That's all. Let's just do the
Just
stop the
words.
process.
That would be it.
Give up.
So how do we find it on disk? Hey, guess what? You'll do that next semester.
Not a hardware.
It's not a
problem.
hardware problem. We
Smiley
don't care.
face.
Yay.
I'll talk about briefly most OSs, and by that I mean only Windows has C and D drive, but everything else uses some logical devices. Real operating systems have a hidden partition that support virtual memory. It's called a swap partition on Unix. It's specially formatted to make this as fast as possible and utilize as much disk space as possible. So it's actually pretty simple. And then you just index the
Unix.
correct page. Unix, Linux,
Go, you
all Nixes.
Nixes are good.
All right, how do we figure out the size of a page table?
Oh, gross.
Oh boy. All right, so for MIPS with a 32-bit address, that means the machine, if the machine can support 1 gigabyte, because when the operating system boots, it does detect how much memory you have, so it can detect how it can adjust different software data structures accordingly. So if you have 1 gigabyte, 2 to 30 of physical memory. We decide pages are of size 4 kilobytes, which is actually very common. 4 or 8 are very common sizes. And then the physical page number is 30 minus 12. I'll make sure this is clear what I'm talking about. Do you remember? This is your page offset. I don't know why I started with an F, but I did. Page offset. And this is the page number. So your page offset, if you're using 4 kilobytes, is going to have 12 bits to the 12th. Okay? So that's
Sure.
12 bits right here.
I call it pages.
And that means your page number is going to have 18 bits left over. Everyone following?
Yeah.
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 Okay. How many bits? Well, 32-bit. You have to go back and you have to use 32 bits because that's the number of addresses. Minus a 12-bit page offset means 2 to the 20 or about 1 million entries. And since it's 18 bits per page number, that would be about 3 megabytes of memory to set up the page table for a process. So before your process loads, it needs 3 megabytes. Does that sound good or bad? Bad. Well, that's a lot, especially if your program doesn't even use a meg, right? We just consume 3 megs just to get it running. And of course, 64-bit probably is going to be a little more. And by a little, I mean a lot. All right. So, whoops. So how do we fix this? Cache it. Thank you. All right, good. But we're not talking about caches. We're talking about pages. So instead of caching the cache, we page the page table.
Page it.
We page it because it's virtual memory.
Do we have a pager?
We could use a hash function, but that means every time you do a load, you have to run a hash function in order to figure out where in your memory you want to go. You all understand what I mean? You're going to have your table here with all the different blah, 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 blah. And if you're going to use a hash function to figure out what block you need to jump to, when you do that load, you have to run a hash function and then jump to it, as opposed to just adding 2 numbers and jumping to the correct entry. And that's going to be significantly slower because hash functions usually do a lot of multiplication, shifting, so forth and so on. So not a good idea, but it does use less memory. You page the page table. So you have one page table that goes over to another page table, which then finally goes into your main memory. I'm just going to use MM. All right? You cache the cache, you page the page table. So you have the super page table. And by the way, you could also do this to where you would page a page table. So you'd have multiple, there'd be another one over here. And that is done sometimes as well. So notice that the address is now broken up. What's that going?
I said, can you page the page of the page
Yes.
of the page table?
Yes. So that's 4. It's turtles all the way down, right?
16.
Yeah.
You can only, well, remember you can only do it a certain number of times because if your address is 32-bit, then you can only do it 32 times, but that would be completely pointless. So now notice we have a super page, a regular page, and then, virtual page, and then page offset. All right, putting it all together. How's your program actually work? Well, ask the operating system to create a new process. So it constructs the page table for it as well as everything else it needs. Mark all page tables as invalid with a pointer to the disk image of the program, that is, point to the executable. Run the program, you get immediate page fault on the first instruction, because by the way, I forgot to tell you, when you try and read or load the first instruction, that's also a page fault, because it hasn't been loaded into memory yet. Cute. All right, this is just how it's done. Oh well.
Oh, well.
You call it and it does stuff.
So let's see, page table indirection enables a fully associative mapping between, yeah. But how do we do LRU? Again, true LRU is expensive because you have to keep track of when everything was referenced, and that can be difficult. But if you approximate LRU, we found out that to be roughly just as good. Reference bit cleared occasionally by the operating system. AKA, you just have a little bit over here, 1 or 0, 0 meaning it hasn't been referenced. And every time you reference it, it changes it to a 1. So what happens is, when it needs to evict something, it just chooses like the first 0 or something and evicts that. And the OS just goes through randomly at random time intervals and just clears them all to 0. That's all. Turns out to be okay. All right, back to performance. Well, we have to translate a virtual address to a physical. We must first access the page table. Then we get an access memory region again. So the load instruction performs 2 memory and a store performs at least 1 read and then a write. So now everything performs at least one extra slow access to main memory. That's the big problem here. Now the issue is that whenever you want to do a load, you're always loading from main memory because that's where the page table is. How could we fix this?
Cache.
Man, you have picked this up, yeah. We could cache it, which is exactly what we do, but we call the cache a translation look-aside buffer. We buffer the common translations in a TLB. We're going to be using TLB a lot. The TLB is the cache that stores some of the common translations. A first cache memory dedicated to storing small subsets of the valid virtual to physical translations. Hey, look, it's just like a cache. It takes a virtual page, which is essentially a tag in the TLB, and if it's there, it gives you the actual physical page. All right? Where do we put the TLB lookup? This is an interesting problem. Let's see, after the virtual address is calculated and before the memory reference is performed. After it's calculated and before the memory reference. So this is, once you have your virtual memory address, you put the TLB before you do your actual load, and then if it gives you the right address, you just do a direct load. Okay, that's really the way you want to normally do it. You could try, some people will do it after the memory read. That can get tricky. Okay. All right. Last thing that's important from a security standpoint, actually the permissions are important. Other translations, well, you have to know where the physical memory is, disk, and unutilized data. Okay, we went through that. Access permission. Some things need to be read-only inside of memory, aka you probably don't want your program to be writing to itself. Also, you don't want a program to be writing or reading from another program, so you also want to put in access information there. Let's see, gathering access information, identify dirty pages. Right, so if a page is dirty and you need to write it back out to, yeah, you got it. Identify accesses to help LRU candidates. Those dirty pages. Okay, VM virtual machine. This is not virtual memory. Sorry, virtual memory system. This is not virtual machine. Virtual memory gives us 2 addresses: virtual and physical. Again, the virtual is what the programmer is using. The physical is what the operating system actually translates it to. Which address should be used to access the data cache? Now this gets interesting, because remember, we now have a TLB and we have a data cache. Well, if you store your virtual memory in the virtual address in the data cache, it's usually faster access. The problem is when you want to write it back to memory, it's a little more complex. You could do just the virtual addresses, which makes more logical sense to us, after the VM translated, but there may be a delayed access because you have to go through the TLB first before you can do a load.
I'm for third option.
No, there is no third option.
Oh.
Sorry.
Hybrid of the two.
Hybrid of the two? Why not both?
Both.
Yeah. It's a trade-off. You just figure out which one's better and do it. Yeah.
Good luck, have fun.
Oh.
If you can hide this delay with a smart processor design, you should do it the physical way. If you're not, then you probably want to do it the virtual way. It just has a lot more architecture in the back end. As we'll see about modern processor design, you can delay this. You can hide this delayed access with certain tricks. We already talked about that. Wait, are we just doing this again? Lovely slides.
No, page replacement.
All right, let's pull it all together. So what's happening here?
Colors.
The colors and stuff. So it's the virtual address is what?
It's going into a table to get the physical address.
Right, but where's the virtual address coming from?
Programs.
The program. So the virtual address is from the program. So it's going into this green block. What is this green block I'm pointing to?
Is it a physical
So
address
it's page
table or
table.
page table?
It's a page table, but more specifically, it's not the big page table, but the TLB.
Right.
Right. So this is the cache, because it's going to a tag to get the physical number, which goes to the actual, which gives you the physical true access address. Sorry. Now that we have this, we can use our data cache to see if it's in there, and hopefully it is in there, and then you can read it back. Everyone got that?
Sure.
Sure.
I'm sure we'll come back to it later.
All right, so what we got perform TLB at the same time as a cache compare. Right, you can do that. Aliasing. What if two processes refer to the same physical location with different virtual addresses? Do we want that to happen? Actually, hold on. Let's ask that first. Do we want that to happen?
That sounds like a bad thing.
Could be a bad thing.
Are we using shared memory?
There you go. If we're using shared memory, then yes, we want to have this happen.
Yeah.
Okay. What problems may arise there?
Reading it after it's been changed.
Well, if you have two different data caches here with two different processes and they're trying to share a piece of memory, could there be any type of deadlock or not
Yeah.
deadlock, but race conditions?
Yeah.
Yeah, race conditions, yeah. We're not going to talk about, we're not getting into that here. That's an operating system. Well, that's actually advanced architecture.
That's above our pay grade.
That's above your pay grade right now, luckily.
Since we're just volunteers.
You're also just business. Yeah, that's it. When you switch a process, the TLD must be invalidated with dirty cache blocks must be written back to main memory. So whenever you do a context switch, the TLB has to be flushed.
Flush it all.
Yep.
Evict it all.
Evict. Evict and flush. Evict and flush.
All right.
I love myself.
All right, what's going on with this one?
I've no idea.
Okay, so this is what's happening if you decide to do the TLB and the data yes.
You just said that the TLB is to be flushed when you've changed programs?
Processes, yeah. Yeah, programs, yes. Because the new process is going to have a different TLB. It's not going to use the same TLB because its virtual memory space is different than the previous process's
right,
virtual
gotcha.
memory. Yeah, because they need to be sandboxed. So you got to flush the TLB.
Go away.
Yep. All right, another way to do this, just to make this even more confusing, is that you could have the TLB lookup as well as the data cache lookup at the same time. And this is your virtual address going to the cache. At the same time, you would have the TLB doing the translation in case it needs to go to main memory. Okay, great. Lastly, you need to have OS support. You must be able to modify the page table register, update the page table values. Should the program ever be doing this?
No.
No, the operating system should be doing it. It would be very bad if the program did it because the OS is what handles setting it all up and sandboxing the different processes. To support this, the operating system, not the user, will have what's called an executive, supervisor, or kernel level mode. Your processors are enabled, modern processors have an enable bit that tell you if you're running in super user mode, or executive, supervisor, or kernel, or you're running in user mode. If you're running in user mode, you can't access the virtual memory as well as other things.
Administrative.
Yeah, administrative rights. And this is a hardware level concept, and this is actually what Meltdown gets around, in a way. Extended example. All right, here we go. Pulling it all together.
Fellows.
All right, what do we have here? Notice the purple is our disk pages. Memory is, was that Aqua? We have a 2-entry TLB, a page table, and physical references. Okay, we got a lot of stuff going around.
Yep.
Well, let's go look at our references. These are the order of references that we're having. We don't care if it's a load or a store. They're treated the same way here. So on the page 1, read the execution header and initialize the page table. So the program is being loaded in. That will just say that piece is reserved for the operating system. The initial page table says you need to go to disk to these 3 spots because we haven't done anything yet. Loads the first reference. Is it in the TLB? Nope, nothing's in the TLB. Go to the memory. Do we have the address in memory? Nope, it's on the disk. Page fault. Take forever to load the memory into the page table. The entry into the page table, and then actually load the memory from the disk into main memory. So now we can service from the TLB the reference. Great. And then why do we have 1,000? Okay, 1,004. That is a hit. Hold on a second. Oh yeah, that's a hit because the TLB, we're assuming we have a very large page table size, so it can go to 1,004 or 1,000. Remember, 4 kilobytes page tables. But this one's going to be beyond the page table length, so that's going to be a miss. There is no mapping, which means that you don't have to pull it from disk. It's just nowhere, so no map page fault. So you go ahead and you set it to zeros, hopefully in main memory, maybe. And then now they're allowed to access it. We go back to 008, it's still a hit because it's inside the TLB. And then that last reference, is that in any of them? Nope. It's on disk, so we got a page fault. Here we go, read it into main memory. Notice that we had to evict M2. Why do we evict M2 and not M1?
You just used M1.
Yeah, least recently used. Move it over, and that should be it. Okay, is that confusing?
Yeah.
Why is it? No, never mind.
Why these are ones? I don't know.
And it added the.
And add one here.
Yeah.
Yeah, it looks like my slide software.
Because memory is reserved from 0 to 1, so you're starting basically.
Oh yeah, that's right. So, thank you. Because memory is actually setting here with 1, so it translated 004 to 1004, which is up here. Now it makes sense. Hopefully you can see that this supports multiple processes since they can all map to different memory regions. And uses a process ID given by the OS as part of the tag. Yeah, multiple processors can run 2 programs at the same time. Each processor has its own cache. I don't know why I'm asking why. Actually, why is this okay? Why is this actually okay? Maybe that's a good question. This is a tough one.
Without using an operating system response.
Yeah, you haven't taken OS, but that's okay. You could run 2 programs at the same time. You have 2 processes. They each have their own data cache. Why is this okay? In other words, why aren't the 2 processes reading and writing from each other? Or messing each other up?
Because they're
You
not.
said it had its own data cache. Why would that wouldn't make any difference?
Yeah,
I mean,
the caches aren't connected. So they're separate
Each
things.
process has its own cache.
So they wouldn't write to each other's cache. That
Yeah, it
makes
wouldn't
sense.
write to each other's caches, correct. So as long as they've been sandboxed correctly, which is what virtual memory is supposed to do, sandbox all the processes, then this is perfectly fine because all their on their virtual memory is being translated to the correct physical address and everything's fine. They may or may not share data. Sharing of code is not a problem because code is read-only, so we're fine. Example, shared libraries in Linux or DLLs. That's okay, you never write to it, you just read, so that's fine. Sharing data can be a problem because what if one processor's cache needs to write to the other processor's cache?
Sadness.
Again, advanced architecture, we use Snoopy caches. But don't worry about that. Yeah, we call him Snoopy. Snoopy. Oh, that was it. Great.
Yeah, we go to the Linus cache or
Little
something.
Linus. He hasn't gotten that egotistical yet. Any questions? No? Okay, great. No. Any-
Questions on the